IB students, today we'll be solving the 8th question that appeared on the Physics HL Paper 2 2024. Without further ado, let's get started. At a distance r from the center of a planet, the gravitational potential due to the planet is Vg and the gravitational field strength is G. Show that gravitational potential equals minus Gr. So how do we do this? Well, let's write the equation for the gravitational potential. The equation for gravitational potential is minus G, mass of the planet, divided by the distance. Okay, if I multiply the denominator and numerator by r, I can rearrange this and I get minus gm r square times r. And if you focus on this term over here, you would realize that this is nothing but the field strength. So we can substitute minus small g times r instead of this. Minus g stands for this entire term, which is the gravitational field strength, and therefore we have proved the required equation. Okay, let's move on to the next part. For the Earth, the variation of the gravitational potential with distance is shown. A satellite of mass 750 orbits the Earth in a circular orbit of radius this. Calculate the magnitude of gravitational field strength and the orbital radius of the satellite. So the distance is 1 into 10 to the 7, that's here, and the corresponding gravitational potential energy is minus 4 into 10 to the 7. So gravitational potential is minus 4 into 10 to the 7, and we can use this equation over here. Vg equals minus Gr to solve for G. That means G equals minus Vg over R, and R is 1 into 10 to the 7. So we can just substitute the values. Minus Vg is minus 4 into 10 to the 7, and R is 1.0 into 10 to the 7. That gives us a value of 4.0, and the unit is Newton per kilogram. All right, that solves the B part of the problem. Let's move on to the next one. The next part of the question asks us to find the gravitational force acting on the satellite. We know the equation of force is mass times the gravitational field strength. The mass of the satellite is 750 kilograms and the acceleration due to gravity is 4.0. So if you plug those values here, we get force equals 750 kilograms times 4.0 newtons per kilogram. This gives us a value of 300 newtons. The satellite is moved to a new circular orbit. The orbital radius of the satellite increases by 2 kilometers. Outline why the magnitude of the gravitational field strength at the new orbit is approximately the same as the old orbit. We know that the equation for the gravitational field strength is negative the potential, gravitational potential over the radius. The original radius was about 10 to the 7 meters, and we are increasing its radius by a tiny amount as compared to the original radius. The new additional amount is 2 into 10 to the 3. This is negligible if compared with the original radius, meaning the equation for gravitational field strength could be written precisely as R plus delta R. The delta R is this section over here. But this is so small compared to R that we can neglect this. If we neglect this term, the equation becomes minus V over R, and it's a very good approximation. And that's why the magnitude of the gravitational field strength at the new orbit is approximately the same as the old orbit. Determine the change in the total energy of the satellite. Let's start off by writing the equation for potential energy, which is minus Gmm over R, and the equation for kinetic energy in an orbit would be half mv square. For v, we can substitute the value of the orbital velocity. You can find this in your data sheet in the field section over here, V orbital square root gm over r. Let me substitute that in this equation. V equals square root gm over r. If I do that, I get a value of half gmm divided by r. Now if you look closely, potential is minus gmm over r and kinetic is half gmm over r. This means that I can say kinetic energy is negative half of the potential energy. This is a very important equation. This tells us the kinetic energy of a satellite that's orbiting is negative half times the potential energy that it has. Okay, so let's clear the section over here. From this equation, we can figure out the total energy of the satellite. The total mechanical energy would be kinetic plus potential. So I can write kinetic is negative half of potential plus potential. That gives me just half of potential. That's yet another important equation. This equation simply says the total mechanical energy of a rotating satellite is simply half its potential energy. Let's place both these equations here. From this equation, we can realize that the change in the total mechanical energy of our system would be half the change in potential energy. That's yet another important equation. Now we can return back to our original problem, which stated that the initial distance, let's say, was r, and the distance increased by an amount delta r. Let's find out the initial potential energy. U initial would be minus gmm over r, while as the final potential energy would be minus gmm over r plus delta r. Using both of them, we can find the change in potential energy, which is final minus initial. So final is minus gmm over r plus delta r minus the initial, which is minus gmm over r. We can rearrange this and put this into a neat format, which is gmm times 1 over r minus 1 over r plus delta r. So here we have the change in the potential energy when the satellite goes from a distance of r to an increased orbital distance r plus delta r. But we want to find the change in the total mechanical energy. That means we have to multiply half to the change in potential energy. Therefore, our final equation would be change in the mechanical energy is half gmm 1 over r minus 1 over r plus delta r. Alright, and that solves our problem. We have all the values required. G is a constant, m is the mass of Earth, you'll find it in your data sheet. M is the mass of the satellite, r is its initial distance, and delta r is the increase in the distance. And that completely solves this problem. You just need to substitute the values. I hope you found this video helpful. If you did, please give me a like and subscribe to my channel. I'll see you in the next one. Happy learning.